So the topic of this talk will be security proofs for key alternating ciphers. So to begin with, let me present you what is a key alternating cipher. So it's a particular class of block cipher which is constructed as follows. So it takes as input an n-bit key k, an n-bit plaintext x, and it outputs an n-bit ciphertext y. And it is constructed from R public permutations, P1 to PR, and from R plus 1 key derivation functions, game 0 to game R, which maps k to 1 keys k0 to key R. And to encrypt x, you simply XOR k0, apply P1, XOR k1, etc., alternatively. Okay, so this is the general form of a key alternating cipher. And the prominent example of this type of cipher is, of course, AES 138. So the main question about this type of design is how can we prove security? And for this talk, security will mean pseudo-randomness, meaning that the block cipher with a random key should be indistinguishable from a perfectly random permutation. Okay? So I guess a general adversary, of course, it's too hard. It would imply to prove unconditional complexity lower bounds. So instead, cryptographers have tried to prove security, to give partial results and to prove security against specific attacks. For example, differential or linear attacks. And for this, you have to use the specific designs of your permutations. For example, you can prove lower bounds on the minimum number of active S boxes, etc., etc. But there is a complementary approach, which would be to prove security against generic attacks. And what I mean by generic attacks, it's an attack that would break all the class of key alternating ciphers independently of the permutations P1 to PR. Okay? And to prove that this design is secure against generic attacks, you use the random permutation model. So what does that mean to analyze key alternating ciphers in the random permutation models? It means that now the PIs are viewed as public random permutation oracles, okay? And the adversary can only make black box queries, both forward and inverse queries to each internal permutation here. So in some sense, it trades complexity of the internal permutations for randomness, and the nice thing is that it allows for a completely information theoretic proof. So it's in spirit, it's a bit like using the random oracle model for public key crypto. Okay? And the only complexity measure of the adversary now in this model is what will be denoted QE. This is the number of queries to the cipher, or if you prefer, the number of plaintext and ciphertext pairs the adversary acquires, and QP, which is the number of queries to each internal permutation oracle. Okay? And in fact, this model was already considered a long time ago by Even-Mansour for only one round, and they showed that this cipher here is secure up to 2 to the n over 2 queries. And in fact, you can use the same key on both sides of the permutation. So in some ways, this is the simplest block cipher you can build from one single n-bit permutation and one single n-bit key. Okay? And just about the wording, from now on, I will talk about the iterated Even-Mansour cipher, and this will be a shorthand for saying analyzing the class of key alternating ciphers in the random permutation model. So from now on, I'll just talk about the Even-Mansour cipher. Okay? So let me now give you an overview of our results. So what's the state of the art previously to this paper? So at Eurocrypt this year, Chen and Steinberger proved that if you assume that the round keys are independent, and if you assume that the permutations are independent, random permutations, then this block cipher here is secure as long as the number of queries of the adversary is less than 2 to the Rn over R plus 1. So for one round, this is the birthday bound, 2 to the n over 2. For two rounds, 2 to the 2n over 3, etc., etc. And this result is tight in terms of query complexity. But the problem is that this assumption here is not really, it's never true for concrete designs, okay? So the main question we ask is it possible to prove a similar bound when now the round keys are derived from an n-bit master key, okay? And or when the same permutation is used at each round, because this is how most concrete block ciphers, key alternating ciphers are designed, okay? And our paper is the first step because we give a positive answer for 2 rounds, okay? So we provide 2 to the 2n over 3 security bounds for 2 rounds. So in more details, we have two complementary results. So the first one is when you keep two independent permutations here. And then we show that the trivial key schedule is sufficient. By trivial key schedule, I mean you can simply XOR the same key at each run. And so we show that this two-run Even-Mansour cipher is secure up to 2 to the 2n/3 queries. And our second result, which is more complicated to prove, is when you keep one single permutation here, the same permutation, okay, then you have to use some non-trivial key schedule. I will explain why in a minute. And so we prove that this two-run Even-Mansour cipher here is also secure up to 2 to the 2n/3 queries. And here, pi can be any fixed orthomorphisms. And an orthomorphism it's a permutation such that k XOR pi of k is also a permutation. So for example, it's used in IDEA, the block cipher. So an example would be, for example, field multiplication by a constant different from 0 and 1. Okay, and in fact, we have a more general result which gives sufficient conditions on the key schedule such that this cipher here is secure up to the 2n/3 queries, okay? And in fact, the key schedule I just showed you in the previous slide is kind of the simplest key schedule you can, which fulfills these conditions here. And we believe that some conditions are not necessary, but just there for technical reasons. And let me explain the title of the talk. Why do we say minimizing the two-run Even-Mansour cipher? That's because this construction is minimal to achieve 2 to the 2n/3 security. If you remove any component, then security drops back to the birthday bound 2 to the n/2. If you remove one permutation, then you're back to the 1-1 Even-Mansour cipher, which is at best 2 to the 2n/2 secure. And if you remove pi here in the key schedule, then the design becomes very self-similar, and you have a very simple slide attack, okay, with 2 to the 2n/2 complexity. And in fact, this slide attack works for any number of runs. If you use each time the same key and the same permutation, for any number of runs, you have this slide attack, okay? So you really need to have some non-trivial key schedule here. Okay, so in the second half of the talk, I will try to give you the idea of how we prove this. So first, how do we formalize the security for the Even-Mansour cipher? So this is a classical security indistinguishability experiment where you have a distinguisher which must distinguish between the real world, where it interacts with the block cipher with a random key, and the ideal world where it interacts with a perfectly random permutation. But here we work in the random permutation model. So this means that the distinguisher also has access to the internal permutation given as a random oracle, a random permutation oracle. So in the ideal world, the distinguisher simply has access to 2 independent permutations, okay? And for this talk, we'll assume that it makes the same number of queries to the cipher and to the internal permutation. Okay, so the distinguisher has access to these 2 oracles, E and P, and it can query E forward or backward, and it can query P forward or backward, okay? And so on and so on. And this gives us what we will call the query transcript, okay? So QE will be the set of queries to the permutation E, which is either the Even-Mansour cipher or in the real world, or a perfectly random permutation in the ideal world. And QP will be the set of queries to the internal permutation, P. And so, like in the previous talk, we'll use the hash coefficient framework. So we consider information theoretic distinguishers. So it's easy to show that the advantage of the distinguisher is upper bounded by the statistical distance between the distribution of the transcript in the real world and in the ideal world, okay? And as in the previous talk, we will partition the set of transcripts into good ones and bad ones. So I will explain in a minute what good transcripts and bad transcripts are. And if the probability to get a good transcript are close in the real and in the ideal world, and if, moreover, the probability to get a bad transcript in the ideal world is small, then the advantage of the distinguisher is small, okay? So we will rely on this lemma. And so the proof is really a 2-step process, okay? Handling good transcripts, or bad transcripts, and good transcripts. Okay, so let me explain what a bad transcript will be in this setting. So for this, I will introduce what we call a bad key. So we have this transcript here, okay, of the interaction of the distinguisher with the 2 oracles. And we say that a key is bad if if the distinguisher can check its compatibility with the transcript. So there are three configurations where it could check if this key is compatible. So first, if there is a query x, y to e, and two values u and v here, such that k prime is equal to the XOR of x and u and of y and v, then the distinguisher can check whether the XOR of these two values here is equal to pi of k prime. And if it's not, then the key is incompatible with the transcript. And if it is, then it's compatible, and it could be the real key in the real world. Okay? There are two other configurations which allow the distinguisher to test, which would be this one and the symmetric one, like this. Okay? So we have three configurations which gives us bad keys. And we'll say that a transcript is bad if it has too many bad keys. Okay? So I don't give a precise definition, but this is what a bad transcript will be. And in particular, we will have to show that with high probability, the total number of bad keys is less than 2 to the n. And the intuition is clear, okay? Because if the number of bad keys is close to 2 to the n, then the distinguisher can simply check if there is a key which is compatible, in which case this is the real world. And if there is no key which is compatible, then it just guesses that this is the ideal world, okay? So how do we upper bound the number of bad keys? So let's focus on the first configuration here, okay? Then it's simple to see that the number of bad keys in this situation is less than the number of triples xy in the query transcript to E, and uv such that x XOR y is equal to u XOR v, okay? And the main insight here is that this value, x XOR y, is random. Why? Because it comes from a query to E, okay? So if it was a forward query, then y is random, and if it was a backward query, then x is random. But in both cases, these values here are random. And this leads us to an additive combinatorics problem, which is called the sum capture problem. So, which is, you are given a set of q values, okay, A, and you are asked what is the maximum values over subsets u and v of the number of triples a u v such that A is equal to u XOR v, okay? So this is how you can decompose A at the sum of two subsets u and v, okay? So it's easy to see that the maximum of mu of A is q squared. And indeed, if A is structured, for example, if it's a vector space, then mu of A can reach this upper bound q squared. But the sum capture problem asks, can you prove a smaller upper bound for a random set A? Okay? This is a subcapture problem. And there is indeed such an upper bound. So when the set A is truly random, then for q less than 2 to the 2n/3, mu of A can be shown to be less than q to the 3/2. Okay? And hence, mu of A is smaller than 2 to the n when q is less than 2 to the n/3. However, we cannot use directly this theorem because in our case, the set A is not perfectly random, okay? It comes from the interaction of the distinguisher with a random permutation. So this is a set which has this form. So we had to extend this subcapture theorem into a new one, okay? Which said that if you have an adversary which interacts with a random permutation E, resulting in a query transcript QE, then the max of this value here, of this number of triples, is less than q to the 3/2 with high probability. And this is exactly the upper bound we are looking for on the number of bad keys, okay? And this is proved via Fourier analysis. Okay, so this is how we handle bad transcripts. So the second half of the proof is to handle good transcripts. And for good transcripts, we are reduced in some sense to a simple to state permutation counting problem, which is you are given two sets of values x1, xq, and y1 to yq, where the intersection of these two sets is small. And you are asked to compare the probability when you draw a random permutation that the composition of p twice of xi sends xi to yi, and this probability here, which is the probability for a perfectly random permutation. And what we show is that assuming that the intersection of these two sets here is sufficiently small, then these two probabilities are close, okay, as long as Q is small compared to 2 to the 2n over 3. Okay, so this is exactly what we need to complete the proof with the hash coefficient technique. Okay, so the proof is an intricate counting, and it's a bit unfortunate because if you think of it, it's really a simple to state problem, which might have a more elegant solution, I think. Let's call it the random square permutation problem, which is simply how many queries needs a distinguisher to distinguish a random square permutation, okay, p squared, from a perfectly random permutation, okay? So how many queries does a distinguisher need? So we conjecture that it needs close to 2 to the n queries, but we don't know how to prove it. And the best attack we are aware of is to find a fixed point of the permutation, because a square permutation, it's easy to show that it has twice more fixed points than a perfectly random permutation. But this attack requires close to the 2 to the n queries. Okay. Okay, so let me wrap up quickly. So we showed in this paper that this true-round Even-Mansour cipher here is secure against generic attacks up to 2 to the 2n over 3 queries. And this is a minimal construction to reach these results. And in my opinion, what makes these results really interesting is that that's the first beyond busted-bound security results for IIS-like cipher that does not require the independent round keys assumptions, okay, which is virtually used in all previous results. And let me just give some open problems. So we have some technical restrictions for our results, so it would be cool to lift them. In particular, we require that the pi is linear, which is a bit odd, but it's for the Fourier analysis argument to go through. But I think it can be removed. And of course, the main open problem is to extend this result to 3 runs and more. And for the moment, we have no idea how to generalize this sum capture problem to a larger number of runs. Okay, thank you.